So good morning, everyone. So myself, Atindra. I am from Bose National Center for Basic Science, Kolkata. So today, what I will be presenting, the title of my talk is non-magnetic spin filter based on single molecular junction. Okay, so this work was done during my postdoc period at Weizmann Institute in Professor Orenthal's lab. So my group is pretty old, so I just joined Bose Institute just 1.5 years ago. So hopefully I'll be presenting new work in my next meeting. Okay, so this is Professor Bose. I think half of the particle of the universe is boson. So this institute is in his name. So we are situating somewhere here in the eastern part of India, so in Kolkata, okay, the city of joy. So today's plan is like that. So first I'll introduce the problem. Then we basically work on the mechanically controllable break junction technique. And what we use other than transport, conventional transport conductance measurement, we use short noise measurement to detect the spin transport. Okay, so that I'll discuss. Then I'll discuss on conductance and short noise measurement in a single molecular junction, two different molecules. I'll show it to you, and followed by result and discussion. And if time permits, I'll show a few slides on my current group activities. So what we are looking at the small like spin transport at the limit of really nanoscale or atomic scale. Okay, so the main question what we want to ask, what is the smallest component that can control the spin transport? Can a single atom control the spin transport, or can you see any change? Okay, can we identify general concepts that will allow the efficient control over the spin transport at the atomic scale? Because we work on the break junction technique, so at the single molecular level, the local orbital structure plays a huge role in determining the charge and spin transport. So we want to use this orbital hybridization to control the charge and spin transport at this atomic scale. Okay, so the motivation is, of course, spintronics at the atomic scale. So for spintronic application, what we know that we need a spin polarized current, right? So spin polarized current, so current spin polarization we can define like I up minus I down by I up total current, I up plus I down. Okay, so for any spin polarized current, what we know that we need either magnetic electrode or strong spin orbit coupled material. So nowadays people are trying to induce spin polarized current in 2D materials by putting strong spin orbit coupling material on let's say on graphene, MOS2 on graphene, and this way people are trying to generate spin current, okay, or manipulate the spin transport. So what I'll show it to you, our goal is not to use any magnetic material or magnetic electrode. We want to use non-magnetic element, like only magnetic component is the molecule, to see the spin transport. Okay, so spin polarized current is common to half metals in solid state physics, and half metals are those which are basically conducted to one of the type of spin and insulated to another type of spin. Okay, so our proposal, like in a naive way, what we want to see, we want to pass like these two sides, let's say the electrode, and this inside we have a molecule with spin split energy level. Okay, we want to pass unpolarized current through this lead, and if you have some kind of structure inside, then you expect probably one of the spin type can go through this. So we should get 100% spin filtering through this. That is our goal, let's say. So this orbital hybridization was studied in like actually in our group, Oren's group, they studied before. I think previous speakers also showed that nickel benzene nickel junction. So in nickel benzene nickel junction, they found a huge enhanced magnetoresistance compared to the pure nickel junction. Okay, then this is happening due to this orbital hybridization happening because of the nickel benzene nickel junction. Okay, then there was one more proposal was that, for example, you can think about why we are not using pure ferromagnetic material to see the spin filtering. If you take a pure nickel, let's say pure nickel, you will not get 100% spin polarization, because pure nickel you have like nickel is d metal, so you have both s and d type of orbitals. Okay, so now only pure metal, this s type of metal, s orbitals is completely unpolarized. So you will not get, you will get probably 30 to 60% spin polarization if you use only pure metal, pure nickel. Now what Oren's group they did, they introduced a oxygen inside this nickel junction, and they found that almost 100% spin polarization using nickel oxygen nickel junction. So what it does, basically it removes the, it blocks this s orbital, and then the transport happens only through d orbitals. Then you will get this 100% spin polarization. So for our experiment, we are not using any magnetic electrode, we are using silver electrode, which is non-magnetic, and we are using two different molecules. One is vanadocene and one is ferrocene. Okay, and vanadocene has both are in the periodic table d metal, but vanadocene has unpaired spin in the unpaired spin, like 3 electrons are there in the d shell, and in case of ferrocene you have s equal total spin equal to 0. So in the gas phase you can say one is paramagnetic, one is diamagnetic. So we take two different molecules, and the experimental technique what we use, the mechanical break junction technique. I think yesterday's talk, Here and Sunlan, both of them talked about this break junction technique. So only difference I will say, we do at 4 Kelvin, everything at 4 Kelvin, and we don't do any lithographic break junction. So what we take a 100 micron wire, like silver or gold wire, then we break at cryogenic vacuum. So it's a very pure environment. And another interesting thing what we do at like we evaporate molecule in situ. Like first we characterize the metal junction at low temperature, and then we evaporate in situ, so that we don't have any kind of contamination. So we can check the pure metal and then we evaporate. Okay, so this is basically the technique. And another advantage is that we are not limited to only pure gold. Okay, generally break junction technique, most of the people use pure gold because of the contamination issue. But as we are working at the cryogenic temperature, we can work with any different metals. Okay, and like platinum, gold, or silver, all this kind of metal we can use, and we can evaporate molecules. So we are flexible to different type of metal molecule hybridization. Okay, so this is the basic technique, and this is one of the characteristic traces, breaking traces of a gold junction, where you can see very nice conductance step. Then we collect almost 5,000 to 10,000 like breaking traces, and we can construct histogram. So in the histogram you can see very nice conductance peak 1, 2, 3 G0, and that histogram is the characteristic of any metal in a break junction. So this is, for example, if you use gold, you will get this kind of histogram. If you use silver, you will get different type of histogram. So histogram is a kind of fingerprint of any metal that you can say. Okay. So now let's come to the our like molecular junction. So this curve, these 3 curves are nothing like, it's called the 2D density plot. Okay. So what you can see here, 2D density plot means you just take 10,000 traces or 5,000 traces, align at a fixed conductance of 4 G0, let's say, and then plot together in a color scale. That's it. So what you observe in a clean silver junction, you see that there is only 1 G0 plateau. 1 G0 means 1 into 2 square upon h. Okay, and these are the few traces of this junction, and you can see very nicely I plot 2 into G0 s. G0 s means e square upon h, 1 spin conductance. Okay, and then you can see the tunneling regime followed by here, from where actually you calibrate our distance. Okay. Then when you see the vanadocene junction, vanadocene means with finite spin, we find very nicely and surprisingly there is a plateau appearing around 0.5 G naught. Okay, 0.5 into 2 square upon h, or 0.5 or 1 square upon h. If you see in a zoomed image, in a linear scale, you can see this is silver 1 G naught plateau, and below this there is a 0.5 square upon h, 0.5 into 2 square upon h. So almost one spin conductance, one conductance channel. Okay, that is itself is surprising. Generally, what you observe in a molecular junction, the conductance is very low, of the order of 10 to the power minus 2, 10 to the power minus 3 G naught. In fact, in our ferrocene junction, we see conductance, most probable conductance of the order of 10 to the power minus 2 to 10 to the power minus 3 G naught. Okay, so generally the conductance is very low, but this is a very high conductance in a molecular junction, and it is 0.5 2 square upon h. So then how do you know, for example, that there is a molecule or not? So we do inelastic electron spectroscopy measurement. I think that we don't need to introduce it. We just do a DIDV measurement at finite bias, and what we sometimes observe that there is a step in the DIDV measurement, and if you take a double derivative, then you get a peak at characteristic energy, and that corresponds to the vibrational energy of the metal molecular junction. Okay, and coming back to the previous speaker, I think he was talking about how do you know experimentally that which configuration the molecule is sitting. So one of the experimental input, we can provide the vibrational energy, because when molecule is sitting in inside a junction, the vibrational energy can give you like they can calculate using DFT the vibrational modes, and then we can match with experiment and we can tell which configuration the molecule is there. Okay, so we can also as we have a sub nanometer or picometer resolution, so we can stretch a molecule or squeeze a molecule and see the vibrational mode is changing or not, like a guitar string. Okay, so these are few example of a vibrational mode stretching, and sometimes we also observe Kondo effect, which is very normal to this break junction experiment, and this is one of the example of the vibration mediated Kondo effect, and that also we observed in this kind of molecule. Okay, so now what we do now after this conductance measurement, what we are interested in, to see the spin polarization through short noise measurement. Now there are three types of noise in solid state physics, and these noises are, one we know that thermal noise, and one we know that's 1/f noise or pink noise, and another is the short noise. So this is basically saying, this graph is showing the three types of noise. Thermal noise is intrinsic to any material. It gives you, the magnitude is 4 kBTR, and it gives you the resistance and temperature, depends on the resistance and temperature, and it does not depend on the frequency. Okay. Now 1/f noise generally occurs in all the systems. It comes mainly because of the two-level fluctuations. Okay. Now this frequency scale can vary from few hertz to few millihertz to few kilohertz, like few hundreds of kilohertz. And short noise is also flat. It does not depend on the frequency. I'll come to that, what is the origin of short noise. And short noise is proportional to 2EI, average current. So if you increase the current, the short noise increases. Okay. So we are interested in this short noise. In fact, I have worked on the 1/f noise in graphene field effect transistor. That was during my PhD work. So if someone is interested, I can discuss. Okay. So so these are the typical magnitude of short noise. Like if you are at 300 Kelvin, then your thermal noise for a resistance of 12.9 kilo ohm, that means H upon 2 square is 14.6 nanovolt per square root hertz, and if you go to 5 Kelvin, the short noise actually does not change with temperature, so short noise remains the same. But if you are room temperature, you will not be sensitive to the short noise. So you have to go to the low temperature to measure it. Okay. So short noise, you can see that room temperature 5 Kelvin, the thermal noise is 2 nanovolt, and short noise is of the order of 7.3 nanovolt. Okay. So we do all our experiment at 5 Kelvin to do that. Okay. So to explain short noise, and in this kind of molecular junction, what we need to understand, this transport is now not happening diffusively. So transport is happening ballistically in this kind of junction, because the mean free path is much greater than the junction length or molecular length. Okay, in this atomic kind of junction. So in atomic junction, you can think about the transport is happening through few conductance channel, like transverse mode. Like it's like a particle in a box problem. So if you confine your system in one direction, then the transport will happen only through few conductance channel, and through Landau-Whittaker theory, you can just take the conductance is nothing but the sum of this transmission. Total conductance will be the sum of this transmission channel. Okay. Now this is G naught here is defined as 2 E square upon H, which is the 2 spin conductance, like 2 into E square upon H. Okay. So now, when do we expect short noise? Short noise is nothing but it comes because of the discreteness of electronic charge. So what will happen if current passes through a narrow constriction of the order of few angstrom or few nanometer, then what will happen? It acts like a tunnel barrier, and electron can either scatter, like it can go through, or it can backscatter. These are the two possibilities. So if you zoom the current in a conductor, like in a constriction, what you will see, this red means I just marked this as an up electron and one is down electron. So if you zoomed it, you find sometimes the electron is present, sometimes the electron is not present. This is the current, if you zoom the current. So this noise is called the short noise. Okay, this is the short noise. Now, if you increase the current magnitude, then the short noise also is proportional to the current magnitude. So what we define, short noise is nothing but 2EI into F. F is nothing but the strength of the short noise, what we call the Fano factor. Okay. So if the Fano factor is defined nothing like tau n into 1 minus tau n. Okay. Like tau n is the transmission into 1 minus tau n, this is the Fano factor, and we have another equation, conductance is G naught into summation over tau n. So we have two equations. Okay. Now there was a very nice work by Warren's PhD student that was published. You can look into it. So using these two equations, you can actually decompose into different transmission channel. So if you measure short noise and the conductance, we have two equations, and using that we can actually get the transmission channel with some error bar. Okay. So what you can think about, if tau n is very small, like your transmission is very small, then you can, from this equation it says that it's very noisy. But if your tau n is close to 1, that means if you have a completely correlated transmission, then your short noise is 0. Okay. So for tau n less than 1, this is very noisy, and this is there is no noise if you have a fully transmitted channel. Okay. Now, how do we measure short noise? We just measure the resistance or conductance as a function of time. That's it. And then we do the Fourier transform, go to the Fourier domain, we calculate the power spectral density. And what we do, we subtract the thermal noise from that and do the bias dependence or current dependence to check the Fano factor. And that's what we measure. Okay. So this is our circuit, and this is one of our characteristic experimental data as a function of bias. So you can see that frequency versus noise power at different bias, and we fit with some theoretical model at high current bias. This short noise is proportional to 2EIF. So from this slope, we can get actually the Fano factor. Okay. So now the question is that short noise people have measured how one can get the spin polarization through short noise. So again we have two equations. So we can represent our data like this is the theoretical plot. Like if you just have conductance in one axis and Fano factor is another axis, you just construct this theoretical curve like this. So this curve means this line, that means you have only one conductance channel, and Fano factor is nothing but 1 into 1 minus tau. So this line is nothing but 1 minus tau. Okay. So there should not be any data in this gray region. That is theoretically, if you have some data in this region, then your experiment has some problem. Okay. Now this calculation, this is the theoretical plot. I am not going into detail. So you just have this theoretical plot, and we get this data. And this is for there is no spin polarization. We are thinking that two unpolarized spins are going. Like you think about the current through a silver or gold, then you will get this kind of noise graph, conductance versus Fano factor. Now if we include the spin polarized channel, then basically in this plot you just have a factor of 2 will be reduced, and here you're talking about you leave the spin degeneracy and you have spin polarized channel, and this line corresponds to one single spin channel f equal to 1 minus tau. So any data in this point in this light gray region corresponds to finite spin polarization. Is it clear? So in this point you have, if you have any data, that means you have finite spin polarization, and that we can on this line actually the spin polarization is almost 100%. Okay. So how much? 5 minutes. Okay. So I'll go a little bit quickly. So this was spin polarization through short noise was seen in mesoscopic system. Like I think few of you know that 0.7 anomaly in a quantum point contact is a very important phenomena in 1990s or 2000, and people have done like this data was from Charlie Marcus group where they found short noise reduction in this area, in this 0.7 anomaly, and they found this the spin origin is there. So there was also Oren's work, and then Professor Richard Brandt work. They also found short noise in a STM breakjunction, STM contacted cobalt and iron. So let's see our data. This is the ferrocene, silver ferrocene, that control experiment we do. We don't expect any spin polarization there. So as expected, these blue data points of the silver ferrocene junction, and we don't see any spin polarization. But when we put this vanadocene junction and we measured really more than 1,000 data here, there are more 1,024 data points are there, these red data points. And you can see that this region has a lot of data points here, and it doesn't cross this forbidden region. And this means you have a very strong spin polarization on many of the data, and some of the data are going really close to this point. So this point means you have a fully open ballistic spin channels. So almost 95% spin polarization, ballistic spin channel we got. Okay. So we can also stretch a molecule and see that the spin polarization changing. This is one of the traces where we stretch the junction, and we can go from like these are the different channels what we can decompose. And we can see after stretching only one single spin channel remains, like other spin channels are not, you don't have contribution. Okay. So we also found one of the signature, this is that formation of the early stage formation of the junction, molecular junction. We have an extra 1.3 G0 peak that originates from the, from that we get the molecular junction. So I'll not go into detail. Now this is the important thing, why this spin filtering originates in this case. So there are two different groups which we collaborated, Professor Alex Moganov and Professor Leo Kronig. Both of them have done calculations on 2 different methods to prove that we have this spin filtering effect. And first of all, this is the binding energy curve, where we find this perpendicular, our junction is mainly sitting like this, perpendicular configuration, this vanadocene molecule, and both are stable, like parallel configuration also stable, but the conductance of the parallel configuration is pretty low compared to this perpendicular configuration. And this is the spin resolved DFT calculation, where we can see that near the Fermi level we have one of the spin channel has a higher transmission, almost close to -1, and another one is almost 0. So that says that we have a perfect spin filtering in this molecular junction. And this is the low conductance. I'll not go into detail, but what is the basic mechanism that we explain through quantum interference through spin polarized channel? So you cannot explain this 100% spin polarization only through like if you consider transport through only vanadium channel like the d orbitals. Okay, so you have to include 3 different channels and their interference, quantum interference. Then only we can explain this 100% spin polarization in this model. Okay, so this quantum interference already you observed yesterday in Here's talk, and there are several papers which only talks about charge transport and quantum interference. Nobody talks about yet the spin resolved quantum interference and spin transport. I guess this is the first observation of spin dependent quantum interference in this work. So we also observe non-monotonic stretching dependence of the spin polarization, and I'll come to this conclusion of this part. Like we observe 0.5 into 2 square upon h plateau in silver junction, and we observe suppression of short noise and spin filtering almost of the order of 100%, that is like ballistic spin channel in our experiment. And we explain this effect using the spin dependent quantum interference. So in the last two minutes, I'll just show my recent work, what we are doing. So this is the previous group, experimental colleague who helped us, and this is my current research. My background is from two-dimensional graphene and other 2D materials, and I also worked on topological insulator. If someone is interested, I can talk to them. So we are now working on the 2D materials like graphene, MOS2, their hybrid structure, low temperature physics, charge and spin transport, and we are exploring many things. So this is one of the graphene on SiO2 substrate. We have developed recently heterostructure fabrication technique so that we can put any layer on top of any 2D layer on top of each other. So this is one example on MOS2 on graphene layer, so that we have developed. And recently we are also working on room temperature breakjunction technique that we have developed, and that is working very nicely. One of the data is like that. This is the gold junction, where you can see that almost 20 plateaus at room temperature of gold, and this is the histogram of gold at room temperature that has been developed. And this is one of the experiment on gold BiPyridine junction, where you expect the conductance to be 10 to the minus 3 G0. So we are just preparing one manuscript on the possibilities of breaking and making process of these 2 molecular junction. And this is my group right now. They're working on few different topics, starting from 2D materials to single molecular junction. And I want to advertise 2 conferences. You are welcome to India. So there will be one conference where David will be talking, IW PhD, and another conference will be in 2020. This is IconSet, is one of the India's biggest conference, and you are welcome to come visit us. And thank you for your attention.